You guys were all waiting for this day when we talked the fundamental theorem of algebra, right? So, on Monday, we talked about this a little bit at the end. Okay, but the fundamental theorem of algebra basically says that if you look at any polynomial, so say you have a polynomial that's x to the 4th power, right? It has exponent of 4. Then that says that we're going to have, basically, we're going to have 4 roots to our equation. Okay, and that some of them might be real and some of them might be complex, and we got to figure out what those are. So we talked a little bit about this on Monday, but I want to, obviously we didn't do any work on it, so let's kind of work through what that actually means, what the fundamental theorem of algebra actually means. Okay, so we're going to use our notes today. We're also going to use a graphing tool and kind of talk about what are all the zeros of our function? What are all the roots of our function? Okay, so in exercises 2 and 4, it says, find all the zeros of the function. So you can see the first one up here, g of x has x minus 2 and then x plus 4 to the 3rd power. Right, so if I wanted to find all the zeros of this function, I know that we have if I want to find all the zeros of the function, basically I make the function equal to 0. Okay, that's how you find the zeros of the function, right? And I know that if I have something times something equals 0, one of those two somethings has to be 0. So either x minus 2 has to equal 0, right? Or x plus 4 cubed has to equal 0. Okay, this one's easy, right? If x equals 2, then this whole thing becomes 0, and then that's one of the zeros of the function. This one's a little bit more tricky, but if I take the cube root of 0, it's just 0. So if x equals negative 4, that's also a root of the function, a 0 of the function, right? So my zeros of the function will be at 2 and negative 4. Okay, so we're good with that, right? One of the things I did want to mention, hold on, let me double check, make sure I tell you the right thing, is that negative 4 actually is a 0 that happens 3 different times, right? So we would say that negative 4 has a multiplicity of 2. That's back from section 2.2. So because this is a cubed root, this guy has a multiplicity of 3. Multiplicity of 3. Okay. All right. So that's pretty easy kind of review. That's review from 2.2. Now let's look at this guy, number 4. We have h of t equals t minus 3 times t minus 2 times t minus 3i plus t plus 3i. Whoa, all of a sudden we're factoring and we have a complex number, boom, right in the middle of our equation. Woohoo, right? So if I wanted to find the roots of this equation, they've already factored it for me, thank goodness, right? And so I just need to set each of these equal to 0. All right, so the zeros of this function, or the roots of this function, are when t equals 3, t equals 2, t equals 3i, and t equals negative 3i. Those are all my roots of my function. Okay? So we're going to have some fun actually figuring out what those roots are, right? Does this make sense? Even though it doesn't look fun, does it make sense? That It's kind of back to our algebra days, right? Whatever multiplied by whatever equals 0. One of those two has to be 0. Makes enough sense, right? Just really quickly, I don't want to spend a ton of time doing this, but if I actually multiplied this back out, what does this look like? Hopefully I can do this in like 2 minutes or less. I gotta make my screen bigger. It's gonna take a while. Never mind. I can't do it in 2 minutes or less. Basically, if I multiply this out, h of t, it's gonna be some t to the 4th plus blah, 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 blah. It's gonna be something like that, but I don't know what that is off the top of my head. I'll say that for number 8 for you. Okay. Okay. So that's how we find the roots of equation. Let's get a little bit more fancy, not crazy fancy. It says in 5 through 8, find all the zeros of the function. Is there a relationship between the number of real zeros and the number of x-intercepts of the graph? Explain. Okay, so we're going to find all the zeros of the function. Okay, but in number 6, you can see that they've graphed x to the 3rd power minus 4x squared minus 4x plus 16. So they've graphed my cubic function, right? I know since this is x to the 3rd power, I should have 3 zeros or 3 roots. And thankfully, on my graph, when I look, I can see that I have one right here, one right here, and one right here. Now, you guys might have young eyes and you can look at your graph. I have them written down somewhere. So it looks like we have a 0 at x equals -2, x equals +2, and x equals 4. So if I plug in x equals -2, x equals +2, or x equals 4 into f of x, I should get 0 as my solution. Okay, so all of the zeros in equation number 6 are real zeros, right? They're not any, there's no complex number zeros. They're all in the real number scheme. So that's good, right? Okay, but then we get to number 8. Of course it couldn't be that easy, right? We get to number 8. How many zeros are in graph number 8? How many times does how many times do we hit 0? Well, I have 2, right? I have one right here and one right here. My pointer is pointing to the other one, right? So I know that I have 2 real zeros. I have a 0 at x equals -2, and I have a 0 at x equals +2. Okay, but because this is x to the 4th power, how many zeros do I have? I have 4 zeros. So that means that I have two zeros that are real, and I have 2 zeros that are complex. Okay, so how am I going to figure out what my zeros that are complex are? Well, I'm going to bust out my old factoring / foiling skills to figure this out. So this is number 8. I have x to the 4th minus 3x squared minus 4. Okay. I can break this up as x squared times x squared, right? And if I have -4 and +1, when I FOIL that, I will end up with x to the 4th minus 3x squared minus 4. Okay, and then if I factor this again, I get x plus 2 and x minus 2, right? That makes x squared minus 4. And then if I FOIL x squared plus 1, I can do x. Oh, wait, I can't do that. I can't factor that. Now, oh, I should mention, on your homework, I'm not expecting you to do this for 6 and 8. For later on, we'll be able to do it, but here I just kind of want to show you. So, I don't know how to factor x squared plus 1, right? I don't know how to factor that. There's a couple of different ways I can figure out. So, I could just kind of, oh wait, I'm trying to use my eraser. One option is I could leave x squared plus 1 because I can't factor it, right? And so what I'm trying to do is I'm trying to figure out what can I put in for x that will make the whole thing equal 0. So either this has to equal 0, this has to equal 0, or this has to equal 0, right? These two guys, the first two, are already shown on my graph. I already said I have a 0 at x equals -2 and a 0 at x equals +2. But what about this last guy here? I'm not able to factor it, so let's see if I set it equal to 0, if I can figure anything out. If I have x squared plus 1 equals 0, okay, that's the same as x squared equals -1. And then if I take the square root of both sides, I need to always remember in PreCalc to do plus or minus, right? So I get x equals plus or minus the square root of -1. What's another way to say the square root of -1? I, right? So another possible root is x equals plus or minus I. Okay, so the roots are x equals -2 and +2, and I and -I. Those are all my roots of my equation. So now I have 4 roots. 2 are real and 2 are complex. One of the things it asks you in here says, is there a relationship between the number of real zeros and the number of x-intercepts of the graph? Explain. So, like in problem number 6, there were 3 real zeros and 3 y-intercepts, right? In problem 8, there's 2 real zeros and 2 intercepts to the graph. X-intercepts, I said y-intercepts, but x-intercepts to the graph. So what is that relationship of real zeros to number of x-intercepts? Basically, your graph is showing you all of the real answers, right? Your graph cannot show you all of your complex ones. Unfortunately, right? We want our graph to show us the complex ones. We can figure out the real ones. We've been doing that for a while. It's the complex ones we want our graph to show us. Maybe there's a complex number calculator out there that could show us that, but I'm not sure where it is. All right, one last thing I wanted to show you with this problem. Again, you don't have to do all of these things for this particular problem, but later on we will. I wanted to show you that we figured out that x could equal plus or minus I. So if we factor, so remember how I said, oh, we don't know how to factor x squared plus 1? Well, actually we do, because if we do x plus I times x minus I, if we FOIL that, we get x squared plus I minus I minus I squared. Plus and minus I cancel each other out, so we get x squared plus 1. So if you want to factor x squared plus 1, we can factor it. We just have to factor it in the complex realm. So x squared plus 1 factors out as x plus I times x minus I. Pretty cool stuff, huh? It's cool, the word you guys were looking for. No comment. You're just so excited to do this, right? Okay, so let's try some more. Now, in 9 through 28, so a big chunk of your work, you're going to find all the zeros of the function and write the polynomial as a product of linear factors. Use a graphing utility to graph the function to verify your results graphically. If possible, use your graphing utility to verify the complex zeros. I tried to look last year to see if Desmos could do it, but I don't know if it could. Maybe this year it can. Every year they add new functionality. So, okay, so let's start with number 10. Okay, find all the zeros of the function and write a polynomial as its product of linear factors. So if you couldn't guess by now, these are not going to be nice, easy things that we can factor. Right, so number 10 is g of x equals x squared plus 10x plus 23. Okay. Can anyone tell me a factor that I could put in that could make 23 and 10? I can't. So we're going to go to our next thing that we remember from Algebra 2 and algebra, mostly Algebra 2, which is the quadratic formula. So do you remember the quadratic formula, which we were talking about right at the end? We were talking about at the end of class. Yeah, Josiah was helping me. So the quadratic formula works for any quadratic equation, right? We have ax squared plus bx plus c. And the quadratic formula says if that equals 0, then x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so in this case, in our equation G, a is 1, right? There's no number out in front of x squared, so a is 1. B is 10, and c is 23. So let's figure out what our roots are using the quadratic equation. So we have negative b, which is negative 10, plus or minus 10 squared minus 4 times 1 times 23, all divided by 2 times 1. Okay, if I do that math, what I end up with is negative 10 plus or minus. So 100 squared minus 4 times 23 is actually, oh, I don't have it sitting out. 4. It's 8. All right. 10 plus or minus the square root of 8 over 2. So if we do a little simplifying, the square root of 8 is 2 square root of 2 over 2, which is negative 5 plus or minus the square root of 2. So that is our root of one of our roots of our equation. Now, how do I write that as a factor? How do I write that as a factor? So I could say that g of x equals two things here. It equals x minus negative, oh, I ran out of room. Sorry. Well, let me take a step back. Okay, if I told you, if I did the quadratic equation, okay, and I just told you that x equals, let's say, plus or minus 3. Okay, if you go to write that as the factors, then you would say that it's x minus a positive 3 times x minus a negative 3. That's how you would write that as a factored out form. Okay, but I don't have a nice easy answer like 3. I have that x equals negative 5 plus or minus the square root of 2. So unfortunately, I have to write that instead, but it's really, we're just plugging in that number. Okay, so if I wanted to write the factors of this equation, it would be x minus negative 5 plus the square root of 2 times x minus negative 5 minus the square root of 2. Okay, the difference between the two is that this is the plus and minus that we did, but we subtract both of them. Okay, then if you actually FOIL this, I know it seems like a total like, whoa, I don't want to FOIL this. But if you would FOIL this, you would get x squared, okay, and then you would get, well, yeah, you're going to end up with the right answer. I don't want to do it. It's going to take me a long time to do it. But if you actually FOIL it, you're going to end back up with this. I wish I had time to sit there and FOIL it back out. All right, how does that sit? You guys like, ugh. Is everybody still here? It sits. It's there. All right. Let's do number, oh, I don't even know which one I like. Let's do number 14. That's not what I meant to do. There we go. Voila. And it's clean. That's not what I wanted to do. Also not what I wanted to do. Okay. Let's try number 14. Oh, by the way, if we would have graphed, sorry. Undo, undo. So we said that the roots were negative 5 plus the square root of 2 and negative 5 minus the square root of 2. If anybody has their calculator, I have my calculator. I'm going to look. What is negative 5 plus the square root of 2? Actually, let me put it on Desmos here. Back to algebra 2. I love that. I love algebra 2. All right. Negative 5 plus the square root of 2 is about negative 3.58. And negative 5 minus the square root of 2 is this. Okay, and if you remember our original equation that we were trying to solve, it's x squared plus 10x plus 23. Okay, and then I need to reset Desmos. Negative 22, 20. That'll work. And sure, that'll work. Oops. There we go. All right, so this is my original graph. Remember, we are trying to find the zeros of this function. That's actually what we started this problem with. It was a whole big complex quadratic whatever. We actually want to find the zeros of the function. Back in algebra 2, right, if I wanted to find the zeros of the function, I'm just basically looking for these two numbers, right? But what we were able to do by using the quadratic equation was we were actually able to find the exact values of this. So the zeros are at negative 3.586, which is negative 3.586, right? And at negative 6.414, negative 6.414. Those are my two zeros of the function. You can see that graphically, right? But we needed to figure out how to make figure out what that exact number was. So unfortunately, Desmos can't tell you that negative 3.586 is negative 5 plus the square root of 2, but that's what it is. Okay, so for example, number 12, if you do number 12 is x squared plus 6x minus 2. Okay, if I go here, I'm like, okay, my zeros are at 0.124 and negative 16.4124. So I know that I'm not going to have a nice, easy factorization, right? I'm going to have to use my quadratic equation to figure that out. And it turns out if you want to try number 12, they are negative 3 plus, that's not also where I want to be. Negative 3 plus the square root of 11. I think. So is that the same number? Oh, wait. All right, maybe I'm looking at my notes wrong. Hold on. I might have done something wrong in my notes. All right, well, apparently, good thing we didn't do number 12 because I did something wrong in my notes to calculate that. Divided by 2. All right, so I did something off. Oh, I have 16. That's my problem. That's just 6. There we go. Now my graph and my number that I calculated add up to the same thing. All right, so now if I go to do number 14, and I'm trying to find the roots of my equation, 14 is f of x equals x squared plus 36. So if I kind of cheat a little bit and I start off by graphing it to look for my roots. What do you notice about this equation? X squared plus 36. Do I have any real roots to this equation? Nope, right? It doesn't cross 0 at any time. So my numbers are all going to be in the complex realm. What do you notice about this one, though, about if it was x squared minus 36, we would really like that, right? X squared minus 36 we know is a perfect square. X squared plus 36 equals 0. We don't know how to deal with that. Right? So a couple things you could do. We can do our quadratic equation, right? A equals 1 B equals 0, and C equals 36. So you could plug that in and figure out the equation. You could also say that x squared equals negative 36, right? And then take the square root of both sides, plus or minus, of course, and you get that x equals plus or minus the square root of negative 36, which is equal to plus or minus the square root of 36 times the square root of negative 1, which equals plus or minus 6i. Right? That's another way that we could figure that out. So the roots of this equation would be x plus 6i times x minus 6i. And if you multiply those out, you'll get x squared plus 36. Okay? So when you do this homework, you gotta put your thinking brains on, right? Okay, I'm just looking and deciding what I want to do next. Who feels like they want to see another example of one of those? Who feels like they want to just try it and see if they have questions? You guys still here? All right. Let's do number 31 from your homework. So I'll write it up on here. I'm gonna give you guys like a 2-minute start after I write it up on here. And I want you guys to see how far you can get on your own. Okay. So the homework, by the way, is 1 through 19 odd, and then 29, 31, 37, 39, and 43. 39 and 43 are actually really, and 37. 37, 39, and 43 are pretty easy. So probably the most complex one is number 31 that you have. And this is on page 144, number 31. This is from your homework. And it is, we want to find all the zeros of the function, write the polynomial as a product of linear factors, and use your factorization to determine the x-intercepts of the graph of the function. Then use a graphing utility to verify that the real zeros are the only x-intercepts. I want to say y-intercepts. Okay, so number 31 is, this is the most complex we're going to get. And you only have one of these that's a cube function. So f of x equals 2x cubed minus 3x squared plus 8x plus 12. Okay. Now, actually, I told you I was going to give you a minute to get started, but the first thing that you have to do, and like I said, this is the only, let me double check before I say this. This is the only cubic function that you have to do. There's a couple that are to the 4th power, but those are actually a little bit easier. So this is the only cubic function that you're going to do. So I'm going to help you with part A, which is how do I factor this? Okay. So one way that you can factor cubic functions is we could say in these first two terms, they both share an x squared. So if I pull x squared out, I'm left with 2x minus 3. Okay. And then my next two terms, they both share a 4. So if I pull a 4 out, I get x. I wrote it wrong. X minus 3. This should be a negative. Okay. X minus 3. No, I get a 2x minus 3. 2x minus 3. All right, and then since these two share the same factor, I can pull those out, and I end up factoring this as 2x minus 3 times x squared plus 4. Okay, so I actually helped you factor this one. So this is the factored form of f of x is 2x minus 3 times x squared plus 4. So now I want you to, I'm going to give you guys 2 minutes, find all the zeros of the function and then write it as a product of the linear factor. So find all the zeros of the function and let me know when you think you've found the zeros of the function. Okay, so did anybody find the zeros of the function yet?
I think I did.
You think you got it? All right, do you want to share what they are, Connor?
Is it 2i and 3/2?
Yep, except what's up with 2i though? It's got two of them, right? So we have, this one's easy, right? That's exactly right though, Connor. So you've got x equals 3/2. That's a real root, right? And then we have x squared plus 4 equals 0. And x squared equals -4, which gives us x equals plus or minus the square root of -4, or plus or minus 2i. So remember, because we started with, this is the one thing to remember, because you started with x to the third power, that means you should end up with 3 roots, right? So you got 1, 2, 3, because we have plus or minus of that, right? That's really good, Connor. So Mackenzie and Greta, does that make sense? Are you still here? Yep. All right, cool. Now, part B, right? Part B says, write the polynomial as a product of linear factors. So if I was going to write this as a product of linear factors, that means I'm going to have f, that's supposed to be an x, looks like a 4. It means it's going to look like this, right? And so, here, hold on, give me 1 second here. Sorry. All right. So I already know that my first one is 2x minus 3, right? But then I figured out this second one can be factored as x minus 2i and x plus 2i, right? Because x minus 2i times x plus 2i, when I FOIL them together, I get x squared plus 4. Okay? So that's part B. C, use your factorization to determine the x-intercepts of the graph of the function. All right, so if I look at this, can you tell me what are all the places that my graph is going to hit the x-axis, my x-intercept? It's going to hit at 2/3, right? It's going to hit at 2/3. Is it going to hit at plus and minus 2i? Nope, because those guys are on the complex plane, right? So if I go to graph this, I have x cubed, nope, x to the third, right? Nope, I can't type today, guys. 2x to the third minus 3x squared. Make sure I'm doing the right one. Plus 8x minus 12, right? Plus 8x minus 12. Okay, so when I graph this, I actually only end up with 1 0 that is real, right? Which is 1.5, which is 3/2. The other two are on the complex realm. Now we have like 2 minutes left. It's always dangerous to Google on here, but we're going to Google. We're going to look for Desmos graphing complex numbers. See if it's a new feature that they added. Oh, complex plane. I don't think this is the right thing, because when you graph on a complex plane, usually the real numbers are along here and the imaginary numbers are along here. So we're just going to have to leave it at that. It's a mystery where those two complex zeros are, but they're on the complex plane. Okay, so that's kind of it. It'll take a little bit of practice, but you guys can do it. Number 39 and 37 and 39 are actually really easy because they actually give you, basically, these are all of the factors. So, before we found, in this problem, we found 3 over 2 and plus or minus 2i. They give you basically the factors, 3, 4i, and negative 4i. So if you were to write a polynomial with this, it would be x minus 3, x minus 4i, and x plus 4i all multiplied together. That would be your polynomial. Okay. And then number 43 we didn't go over. So if you do not know how to do 43, you can try 43. But if you don't know how to do 43, you can skip over that one. But these guys should actually be pretty easy because they basically do all the hard work of factoring. You're just rewriting it. So, all right, that is it, guys. Thanks for sticking with it today. I know it's kind of complex, right? And this chapter is just kind of like a really kind of stretching kind of chapter. The next chapter we're going to talk about, I forget what the next chapter is. I have it on there somewhere. But then chapter 4, we actually start into trig, which is kind of a completely different thing. So if this feels like crazy hard and you're like, oh, is the rest of this going to be like this? No, the answer is no. We're going to have a little bit more of this kind of heavy analysis of roots and that type of thing. And then we'll be moving on to some other things that stretch your brain in different ways. So, all right, guys, have a great day. Let me know if you have any questions. Enjoy those quadratic equations, and I will talk to you guys soon. Bye, guys. Thanks.